All right, before moving on, though, we're going to have to look at something that deals specifically with environmental science, and that's a natural experiment. So not all experiments can be done in a controlled environment. So, for example, it'd be extremely difficult to study the interactions between a wolf and caribou populations because we could not get this controlled setting. They both need large amounts of land. Wolves, will cover vast quantities of an area, and there's no possible way you could do this in a controlled environment. Even in zoos, we don't really understand animal behavior in zoos because it's not their natural habitat. So we call this a natural experiment. And what sometimes we get lucky, and we can certain things can happen to an area like a volcanic eruption. On the right here is Mount St. Helens after it erupted in 1980. But this is a great example, or a volcano is a great example of a natural experiment because it provides us with understanding in a large scale area. I mean, the last thing you want to do is wipe out an entire forest and then see how it comes back. So what Mount St. Helens did was allow us to see the progression of a forest in the area that it was cleared. So again, natural experiments are found, and the problem is the results can be very difficult to interpret because, again, we don't have this control. There's many variables, and in order to do this, we have to observe areas that were not affected. But we'll run into a lot in environmental science. So we have to use reasoning. There's two types of reasoning when we are interpreting our results. There's the inductive. It's these specific measurements that arrive us at our hypothesis, and it's a bottom-up approach, whereas the deductive reasoning, what we're doing is we're using logic. First, we're getting a conclusion based on a generalization or a premise or what we understand, and it's a top-down. Here are the two. With inductive reasoning, you're starting with an observation and working your way up and testing your hypothesis and maybe developing a theory, whereas the deductive, you're starting with a theory, and are you going to confirm it or not? That's the question. I don't know if you're big fans. We all know about Sherlock Holmes. Maybe you saw this show in the mid-2000s, early 2000s, and they're flipped from the previous slide. So just notice inductive reasoning is on the left here, deductive on the right, and of course, to make it inconvenient, they're switched up here. But it helps out because Sherlock Holmes was a deductive reasoner. He would come up with this theory, form a hypothesis, do his observations, and then confirm if his theory was correct or incorrect. Again, I don't know if many of you have watched House MD, the show, but he would develop this theory, go back, observe the patient, look for patterns, get this tentative hypothesis, and move back to his original theory, either dismissing or accepting it. So an example in environmental science is, notice I'm making observations. Perch have fins, walleye, all these fish have fins, and my conclusion is all fish have fins. That's inductive reasoning. Opposite of that, again, is deductive. We're starting, remember, with a theory. In this, my theory, all birds have feathers. I see an eagle. Eagle has the feathers, which makes the eagles are birds. So just know the difference between those two types of reasonings. Then what we need to do is disseminate our findings. And we're going to get in more detail this as we go on here, but nothing is ever proven in science. All we can do is keep collecting data, keep replicating experiments, and supporting theories. So this hypothesis, if it's supported many, many times and the results keep coming back the exact same with different people doing the same experiment, we develop a theory. And then all well-supported theories become natural laws. And these are things we are just can't get around. So the conservation of matter, gravity, for example, is a law. So that's how we get our findings out. And again, this might not seem so, or might take you off a little bit, but there are no facts or truths. We just have these observations. We have data. And at the end of the day, data, especially numbers, don't lie. So we cannot prove something to be true. We cannot say fact, truth, or proven. But again, if 97% of scientists say that global warming is occurring due to human actions, 97% is a pretty good good number that we are part of the problem. If something were to happen 97% of the time, you came to school and failed a test, you're not doing so well, you're probably not going to pass school. So again, those numbers are what we rely on for our data. Looking at our baseline, we're going to look at these four individually in detail right now. First, we're going to start with our baseline, and again, that's this, we don't have this control. Subjectivity of humans, interactions of humans, and notice we're always kind of the one involved presenting these challenges in environmental science. So going to our lack of baseline data, what we mean by this is that we don't have another Earth to compare it to. We don't have, in the graph on the right, just these temperatures going back more than 50 years. We don't have long-term data. So again, there's no control Earth. So for example, we can dig ice cores in Greenland and find lead that was produced by humans hundreds of years ago. PCBs found in plastics are now found in the fatty tissue of penguins. And then even invasive species from early explorers. So what we need to do as environmental scientists is we need to speculate, since we don't know what the original Earth and conditions were like before humans. Another problem we run into is subjectivity. How do you look at something? You've all maybe gone grocery shopping and been given the option paper or plastic. Which one does have the least impact on the environment? To create that paper bag, they did have to use a decent amount of chlorine that ends up in our waterways. To make the plastic, they use benzene, which is a toxin. So, how do you look at it? Is chlorine in the water affecting fish, or benzene, or burning petroleum to make the plastic? These involve judgments and values and personal opinions. And at the end of the day, there's no right or wrong answer. Another example we talked about was DDT. It's horrible. Eagles' eggs were becoming soft and they were becoming endangered. But then again, mosquitoes carry malaria that could affect the human population. So again, where do you side? And it all goes back to this subjectivity of personal opinion and values. So sometimes there is no right answer. Looking at interactions. In regards to interactions, give me a moment. Most of the systems on Earth are intertwined. They're affecting each other. The water cycle is involved in the carbon cycle or the nitrogen cycle. And we can't just study one system easily on its own. Perfect example, we have to create models and to understand that things get complicated in regards to systems. And what happens is when they function, going back to that interacting with each other, we can't just focus on one specific interaction. So we have to take for consideration that all these other systems are occurring at the same time. Human well-being. In regards to the human well-being, we have to understand that, we have an impact on the biological and natural resources of this world. And we all know certain people in the world there's not an equity between the standards of living across the world. Example of that is I'm someone who has a difficult time day by day getting their basic needs filled. And when I say basic needs, that's food, water, shelter. Someone who's struggling to meet those needs, the last thing on their mind is energy consumption or pollution or fossil fuel use. So this human well-being aspect is a challenge in environmental science as well. And finally, we have these parts of a system. There's things coming in regards to energy. A lot of it involves the sun. And then what happens as the energy goes through the cycle? This could be a food web. This could be the water cycle. And then sometimes it's stored. We'll see a lot of the carbon that is was initially put into the atmosphere, a lot of it was stored in shelled organisms. They evolved to create their protective shells out of that carbon that was in the atmosphere and then dissolved into the water. And then eventually, how does it get out? So it's this system, and you've seen the models with the arrows of things going in, things coming out, and they're very, very complicated because this nitrogen cycle doesn't occur in this small area in the picture. It's a worldwide phenomenon. So they're still just more simple, though, to create and to get the message across on how the natural world works. And we're going to end up here, and there's two types of science. Our first one is the frontier. Think of, when explorers or pioneers were moving west, they called that the frontier because everything was new and we didn't really know much about it. So these are the newer theories. When we say they're often contentious, that means, there's a lot of skeptics out there. And notice evolution was on the frontier in the 1800s. It is now on the consensus side. And when we say consensus, that means, again, that 97% of scientists agree that global warming is human-induced. That's a consensus. It's not on the frontier anymore. So those are things like the laws of motion. Now, again, we've come far enough through more experiments and more data, more research in regards to evolution. Evolution is now a consensus. Yes, global warming is a consensus. So know your two types of science. Again, frontier is more the new age stuff. Consensus is what's been around, and that scientific method, those experiments keep going back to the same conclusion. That wraps up our lecture on studying the state of the earth. As always, you have the website. You can go check it out. We'll see you later.